So to solve P versus NP, I'm going to show you an example using a Rubik's Cube and some grid paper. Okay? So right here, I'm going to get me a nice 12-point brush. Yep. And I'm going to start with the number 3. Okay? Number 3. 1, 2, 3. What does this 3 represent? Let's say it represents the green side. Okay? Let's say it represents the top row of the 3 green. The top row, right here. 1 unit, 2 units, 3 units. Okay? So, we know that that is this relationship right here. 3 squares is the same as the 3 top rows of a Rubik's Cube, for example. It doesn't have to be 3, but in this case it is. What does this 3 squares tell us? What do we know every time we see 3 squares like this? Well, we know that beyond those 3 squares is the red color, right? We know it's the red color when we get red. Right? We know it's the red color. So how do we draw the red color? Well, just like real life. We go from this point to that point, right? And then we go over 3. So from here, 1, 2, 3, and then back to here. Okay? And then when we connect the lines, it's a little fat, but when we connect the lines, we get this shape. Poorly drawn, because I think I put this dot in the wrong spot. It goes right there, and then it goes here. And then we can draw the line. Right? Like that. Okay? So we know that this shape, this weird rhombus shape, is the same as the entire surface of the top of the cube. Right? We know that it is the entire surface. And what's interesting is we know, just from reality, right? We know that extends 3 cubes. But there's a catch here. There's a catch. It extends 3 cubes, but from here we see that when we tilt it, the distance is perceived as only 1 cube. Right? I have this line here. It's a little poorly drawn, but I got this line here. Right? Horizontal. And where's the distance of this here? Well, it's up 1, over 1. That is a single unit. Like, this front corner and this back corner are presented as though they are 1 unit apart. This is what they call general relativity. Okay? So that's in that way. For that reason, we know we have this shape, and even though we can't see exactly how many squares are in there, we can figure it out, right? This red, this is P. Okay? This red is P. Now, you ask yourself, what is the green? the green is N. Green equals N. And then you say to me, how does P times N equal, how are they the same? Well, what is P? P is equal to 4, right? We know P is equal to 4. We know P is equal to 4. Why is P equal to 4? Because the red occupies 4 distinct units of space. Okay? What is N? N? Well, it occupies 3 distinct units of space. Now, here's where it gets interesting. We know that red P equals what? We want to prove red P equals NP, right? How do we do that? Well, look at the shape of red P. What is important about this shape? The reality is, this shape is made up of 1, 2, 3, 4, 5, 6 triangles, okay? Which means you can take each of these halves and you can put them together as a single square, right? You can take the halves away and then reform them together and make a single square, kind of like the green rectangle. Which means, although this occupies 4 units of space, it also occupies 3 units of space, which gives us, we'll call it orange P. Orange P occupies 3 units of space. 1, 2, 3. And why is it like this? Why is it only these 3? Because when we're in comparison to the front of the cube, right, you'll notice this top corner, this top half, is not in line with the front face. But if you look at the back half, poorly drawn, the back half is in line with the front face. Okay? For that reason, we have a second P. And in this particular instance, this P is also 3. So when we have N, I wrote 4, this should say 3. When we have N, which equals 3, red P, which equals 4, and gold P, which equals 3, right? We say red P equals green N times, get black for that, times gold P. So in this instance, red P is 4, N is 3, so 4 times 3. Oh, so like, here's what we're saying. Okay, we're saying red P, which is this square, an entire face, is the same thing as the basically the x times y, N times P, which is basically going in the diagonal direction, right? Gold, like if I'm looking at this cube here, gold P is this white top row. That's what gold P is, okay? So there you have it. This top surface is the same thing. Top surface P equals north I don't know, equals this times that, which is, in this instance, 3 times 3. P equals NP. There's your proof. This face is the same value as that face. The front is the same as the top. Now you can get more interesting with this. You know, there's a certain equation you can do to get more validation here, right? How do I prove that P equals NP for real, right? Well, you must understand that the cube is both light and it is matter. It is both mass and light. So when I take this 3 here, this 3, this n, is the speed of light. Let me get this. N is the speed of light, 3. And because we know 3 goes in the gold P direction as well, which we can calculate over here, it's typically, if we know it's to be squared, it's 3 squared. And it's squared because it goes in 2 directions, okay? So 3 squared times red P, 4, right? What does this give us? This gives us an absolute cube, right? Like if I take out this calculator, just so you know I ain't that stupid, 3 squared times 4 is 36. 36 is the number of points and corners on a cube. So that's the first half of MC squared. And because of the law of equal and opposite reactions, and because it's truly C squared, you do minus 3 squared again. So then we take our 36 and we say minus 3 squared, and that gives us 27. And he's like, okay, P equals NP, which equals 27. And how do we know this is true? Well, if we look at the Rubik's Cube, what's the classical way of solving for the entire volume of a Rubik's Cube? Well, it's 3 times 3 times 3, right? And what is 3 times 3 times 3? Well, it's 27. So there's your proof. There's your proof that P equals NP, or NP, one of the ways.